Hi everyone, this is lesson AD4 and this is about the derivatives of inverse functions. So let's start with a quick review. If you have two functions f and g is the inverse of f, right? Remember that f inverse is written like this, inverse of f. This does not mean f, when we write f -1 like that, x, right? This is not 1 over f of x, right? It is not this. What it means is the inverse of f. So f inverse is going to be the function that undoes whatever f does. So here, if you have a table of values for f, then it says, can we create a table of values for g if g is f inverse, right? So if you remember from Algebra 2, you create a table of values for g simply by swapping the x and the y values, right? So if I were to write x and g of x, then f is the function that takes in -3 and gives you back -26. G will be the function that takes -26 and gives you back -3. So if you just swap the ordered pair, and put these y values of f in as x values for g, then you would have created a new function which undoes whatever f did. So swapping is how we understand inverse from a table of values. If you have a graph, right, then if you remember this also from Algebra 2, first of all, to have an inverse, we can say an inverse exists if f is 1 to 1, okay? If f is 1 to 1. What does that mean? That means that if you have the parabola, for example, here in this equation, f is equal to x squared, this is not 1 to 1. This function does not pass the horizontal line test, right? So this is not a 1 to 1 function. It will not have an inverse. However, if I restrict the domain and I say that I only want the part of the parabola for x greater than 0, so I make a function f that looks like this, then now this passes the horizontal line test. It is a 1-to-1 function. That means that every y value, there's only one x value that it came from. And so this will have an inverse, and the inverse will be graphically the reflection of this graph across the line y is equal to x. So if you draw the line y is equal to x and you reflect the f graph in that, then you would have made the f inverse graph. And the f inverse for this particular restricted domain parabola is going to come out to be the square root of x, because we know that that's how you undo a squaring, okay? The last way I want to talk about inverse, which you've done before in Algebra 2, is the equation. If you ever need to write an equation for f inverse, then what we're saying is that right now, if this is your f, then y is equal to x cubed plus 1. So to get an equation for f inverse, you swap the x's and the y's, and you solve for y. Okay, so if ever you need to get an equation for the inverse, then that's what we need to do. Okay, so let's move on now to the calculus. The calculus is going to be about derivatives of inverse functions. And something we need to realize also about inverse functions is every function is a mapping. So that means it's like an input-output box. I take in x, and the function f gives me out f of x. Now, if g is the inverse of f, that would mean that if you string this g function here, what comes out of g will be x. In other words, if you do the two functions one after the other, nothing happens. You start with, for example, if f is x squared with the restricted domain, and g, we know the inverse of that is square root of x, If I put in the number 2 here into f, I get out 4. If I put 4 through the square root of x, I get out 2, right? So when I cascade these functions, when I do a composite function f of g of x, or if I do g of f of x, it works both ways. If those functions are inverses, then the net result will be nothing, right? So nothing happened because you do the two things together, you just get out x, okay? So remember that if the question says f of g of x is equal to x or g of f of x is equal to x, either way, this is another way of saying that f and g are inverses, okay? So if we have a one-to-one function, right, f, and that means it has an inverse, and if this function is differentiable, and that just means that it's smooth and we can find a tangent line everywhere on f, then the inverse function g, first of all, will also be differentiable, and second of all, we can write this equation for the derivative on g, which says that g prime of x will be 1 over f prime of g of x, right? And f prime of x will be 1 over g prime of f of x. And that's the equation that we're going to try to understand and use today. So in the last lesson, you guys learned that the derivative of ln x is equal to 1 over x. I want to take a minute to prove that to you using what we just learned about inverses. So we know that e to the x and ln x are inverse functions. So when I think of e to the x, remember I told you, just remember 3 points. E to the 0 is 1, and e to the 1 is about 2.7. That's e, right? And then e to the negative 1 is about 0.4. So e to the negative 1 is going to get you around here. This is negative 1 comma 1 over e. This guy is 0 comma 1. And you connect these in that hockey stick shape, you have your e to the x function. ln x is the reflection of this across the line y is equal to x, which means every ordered pair gets swapped. So you have 1, 0, and then you have e comma 1. So I go out about 2.7 and up 1. And then 1 over e, which is about 0.4, and I'll be down to negative 1, right? So just remember those, and you get a pretty decent graph of e to the x and ln x. E to the x has a horizontal asymptote on the x-axis. ln x has a vertical asymptote on the y-axis. Okay, so these are inverse functions. Now, let's think about what that equation that we just had in the box means. So what it said in the box is that g prime of x, so in this case, let's say our g of x is the ln x and the f of x was the e to the x, right? So they're inverse functions. Then g prime of x will be 1 over f prime of g of x, right? So what are we saying? We're saying that if we want to know the slope on the red function here, the ln function at, for example, e, for example, I want to find this slope of the tangent line right there, right? All that I have to do is go 1 over f prime of g of e, right? So 1 over f prime of g of e. Well, g of e means the y value here on g, right? So I'm really doing 1 over f prime of 1. And f prime of 1 means the slope over here. F prime of 1 means the slope right there, right? So I just wanted to show you that that's really what this equation is telling us. It's saying, for example, in this pair of functions, the blue and the red, they're inverse functions. So the derivative at any point, like I picked this point e comma 1, right? So the derivative on that point, the slope of this green tangent line here on the red graph, is going to be 1 divided by the slope of the green tangent line on the blue graph. So we go to what I call the companion point. There are, like, every inverse pair of functions has companion points. You know, 1e goes with e1. So the slopes at those two places are related by a reciprocal. In other words, if the slope here is e, which it will be, by the way, because the derivative of e to the x is e to the x, so the slope right there is e, then the slope on the companion point on the inverse graph is going to be 1 over e, right? And that's what we get also if we take this equation further, 1 over e. G prime of e is 1 over e, and that's 1 over f prime of the companion point. Okay, so that's one thing I wanted to say about this. The other thing I want to show you is how do we get this equation ln x derivative is 1 over x. You can just start with the equation e to the ln x is equal to x. By the way, this is like saying f of g of x is equal to x. That's just a statement that the two functions are inverses. And then you can differentiate both sides. And you would get this on the right is just 1, and this over here is a chain rule. The inside is ln x, and the outside is e to the x, right? So out prime is e to the x, and in prime, I don't know. That's what I'm trying to prove to you, that that comes out to be 1 over x, right? So we'll just say we don't know what the in prime is. So we'll call it d dx of the in. That's all we know. We'll call it that. So then out prime of in becomes e to the ln x, right? And then in prime, I don't know what it is yet, d dx of ln x. Well, e to the ln x is just x. So d dx of ln x then becomes 1 over x, right? So that's just a little proof for you that what you learned in the last lesson can be actually proved using the inverse derivative rule. Okay, so let's do some problems now. Suppose p is a differentiable function and the table gives values for p and p prime for x is equal to 4 and x is equal to 5. So we've got 4 and 5 as our x's, and we've got p and p prime. Find j prime of 4 where j is p inverse of x, right? So we could just say we know these are inverses, so j prime of x, in this case we actually want j prime of 4, so I'll put in 4 here. J prime of 4 is going to be equal to 1 over p prime of j of 4, okay? J of 4, now I have to think about that. We can look here and we see 4 here, right? So p of 5 is equal to 4. Well, if these are inverse functions, then you have to realize you're being also told that j of 4 is equal to 5. So then I'm just doing 1 over p prime of j of, sorry, 1 over p prime of 5, put in the 5 here, right? And so p prime of 5 is 9, and my answer is 1/9, right? Okay, you can pause the video and try another one. Try to find j prime of 10. So for j prime of 10, I'll say this is equal to 1 over p prime of j of 10, right? J of 10, I see it right here. You have to look for a y value on p, which is equal to 10, and that then gives you j of 10 is equal to 4. So then this is 1 over p prime of 4, and p prime of 4 is 8, so the answer is 1/8. Okay, so that's how we work a table problem. Let's talk about a equation problem. Okay, so I'm going to do example 4 now. Example 4 says that f of x is equal to rad x minus 4, and g of x is the inverse. So that means is equal to f inverse of x. And we're asked to find g prime of 1, right? So the steps for a problem like this will be first to realize that we can use the equation g prime is 1 over f prime of g of 1, right? G of 1 means the y value on the g graph at 1, right? So that will be, this is the g graph. We're at the point x is equal to 1, y is equal to g of 1. That means on the f graph, the companion point is going to be g of 1 comma 1, right? So because the points get swapped. So I just have to find the x value on the f graph when y is equal to 1. So then I just can take the equation for f, which is rad x minus 4, and set it equal to 1, right? This is equal to f of x. So if my y value is equal to 1, I just make the y 1, and then I square both sides, and I find x is equal to 5, right? So that means that this number here on the f graph is 5, which means that the y value on the g graph is 5 when x is equal to 1, right? So then I can come back to my equation, and I can just do 1 over f prime of 5. Now for f prime of 5, I have to first find f prime of x. And for f prime of x, I'll use a chain rule, and I'll get 1 over 2 rad x minus 4. Then I'll do f prime of 5, 1 over 2 rad 5 minus 4, which is 1 over 2. And my final answer here will be 1 over 1/2, which is equal to 2. Okay, so that is example 4. Okay, so now we have example 5. So for example 5, g of x is equal to, or sorry, f of x is equal to tan x. And then we're asked to find, well, g is given as the inverse of f, and then we're asked to find g prime of 1. So we'll start with g prime of 1 is 1 over f prime of g of 1. Then we know that on the g graph, I'm at the point 1 comma g of 1. So the companion on the f graph is going to be 1 as the y value, and we're going to try to find our x value. And that x value will be g of 1. So I know that the function is tan x. So I'll say tan x is equal to 1, and I'll solve that. X is equal to arctan, or tangent inverse of 1. That means x will be pi over 4. I'll stay within my restricted domain, right? And I get x is equal to pi over 4. So this is pi over 4. That means on the g graph, my g of 1 is pi over 4. So then I'm just doing 1 over f prime of pi over 4. And then I go to the f equation. F of x equals tan x. So f prime of x is equal to secant squared of x. And f prime of, what did I need? I needed f prime of pi over 4. So I do secant squared of pi over 4. That's going to be 1 over cosine squared of pi over 4. Cosine squared of pi over 4 means I take cosine of pi over 4 and square it, and I get 1 over 1/2, or 2, as my answer for f prime. So then I come back to my equation, and I say g prime of 1 is 1 over 2. So final answer is 1/2 for example 5. Okay, now we have examples, sorry, that was example 4. I think I said the numbers wrong. But anyway, we're now on this example, example 5. And in this one, we're trying to find g prime of 4. So same basic idea, g prime of 4 is 1 over f prime of g of 4. So then that means that I need to put in 4 as my y value on the f and try to solve this equation, right? Now, when that equation is something that doesn't look easy to solve, like I am not quite sure, you could try to, put everything on one side and see if you can factor it, but this one doesn't look like that would work. I just want to remind you that solving an equation simply means finding an x value that works. So if you just plug in some simple numbers like 0, 1, -1, you can sometimes find a solution to the equation pretty easily. In this case, if we plug in 1 cubed plus 1 squared plus 2 times 1, we get 4, which means x is equal to 1 is a solution to this equation. So then that means that my g of 4 is equal to 1, and I can come back over here to this guy and say I'm doing 1 over f prime of 1. To get f prime of 1, you first find f prime of x, which is 3x squared plus 2x plus 2, and then you put in 1. So f prime of 1 is 3 plus 2 plus 2, which is 7. And so my final answer will be 1 over 7. This last problem, it's just information is given to you with just a statement like this, but it's really similar to the table problem. So if it helps, you can make a table, because what we've been given is f of 5 is 20, f of 7 is 5, f prime of 5 is negative 4, and f prime of 7 is negative 5 halves, right? So you can make it into a table problem, and then if we're looking for g prime of 5, it's 1 over f prime of g of 5. So g of 5 means we look for a y value on f equal to 5, and so now I know that g of 5 will be 7, and so then this is 1 over f prime of 7, and then f prime of 7 from the table is negative 5 halves, so 1 over that is negative 2/5. Okay, this last one I'm going to show you for inverse, general inverse functions is this graph problem, and it says that the graph of a decreasing differentiable function f, should just say f, is above or here to the right. Also shown is the line tangent to f at the given point, I guess, right, or at the point 3, 6. Let g of x be the inverse of f. Which of the following statements about g prime is true, right? So first I want to mention that when a problem says this kind of thing, that it's a decreasing differentiable function, the decreasing is there to tell you that if a function is always decreasing, right, then it must be 1 to 1, right? So that's what they're telling you there. So this is code for, has an inverse. This function has an inverse. You're allowed to use the inverse formula. Differentiable, remember that's also something that has to be true for you to use the inverse formula. So here we are, we're trying to find, we're given this point here, 3, 6, and so on this f graph I have a point 3, 6, right? So on the g graph, which I don't know, I'm sorry, it's 4, 6. It's 4, 6, my bad. So this is 4, 6, okay, 4, 6, okay. So remember that I have information about f prime of 4, and I can then say that g prime of 6 is going to be 1 over f prime of 4, right? The companion point on the g graph, the companion is going to be 6, 4, and the derivative here on the f graph, this slope of this tangent line looks like, let's see, we are like, looks like, 3 down for 4 over, right? So I can say f prime of 4 is equal to negative 3/4, right? The reciprocal of that will be the derivative of g at 6, right? So g prime of 6 will be 1 over negative 3/4, which is negative 4/3. So that's what we can say, and we just find the equation that says that, and that would be choice C. Okay. All right, the second part of this lesson is about a specific class of inverse functions, which are the inverse trig functions, and we need to find formulas for the derivatives of the inverse trig functions, right? So I want to remind you, arc sine means the same as sine inverse of x, and we are in the domain negative pi over 2 to pi over 2. Arc cosine means cosine inverse, and we are from 0 to pi is the restricted domain. And then arc tangent, your answer has to be between, again, negative pi over 2 and pi over 2. So we practiced this when you did the little unit circle quiz a little bit, or on the pre-calc packet. So how do we go about finding the inverse derivatives? Well, let's try to prove one of these, or maybe, yeah, we'll prove one and then you can prove the rest for yourself. But if I try to prove this first one, right, let's think about the derivative of arc sine of x. So what we can do is start by just the equation that sine of sine inverse of x is equal to x. That's just the statement f of g of x is equal to x, right, which is true for any two functions that are inverses of each other. Then I can take the derivative of both sides, right? So I'm doing d dx of this side and d dx of the other side. On the right side, I just get 1. On the left side, I have an outside function, which is sine of x, and an inside function, which is sine inverse of x. I don't know the derivative of the inside. That's what I'm trying to find. But I do know the out prime. The out prime is going to be cosine, and out prime of in means cosine of sine inverse of x. And then I would have the in prime, which is the derivative of sine inverse of x. And this is what I'm trying to find. So let's go off here and draw a little triangle. By the way, I should do one more step here. So before I draw the triangle, that means that the derivative of sine inverse of x is equal to 1 over cosine of sine inverse of x. So I'm dividing both sides by this factor, okay? So how do we find this cosine of sine inverse of x? Well, if we draw a little triangle, right angle triangle, where the sine of this angle here, this green angle, is x, then it would have to be the opposite side is x and the hypotenuse is 1. Now, the sine of the green angle is x. So if I write the length of this side here, that would be by Pythagoras theorem, 1 squared is equal to x squared plus whatever this length is. And I would get that the length is 1 minus x squared, the square root, right? So this length right here of this side is 1 minus, the square root of 1 minus x squared. So now if we remember what sine inverse means, sine inverse of x means this angle, right? It means the angle whose sine is x. So this angle is sine inverse of x. And if we're taking cosine of that angle, then that just means adjacent over hypotenuse, which would be rad 1 minus x squared over 1, right? So this whole thing in the denominator is just rad 1 minus x squared over 1, or just rad 1 minus x squared, which means we've just proven that the derivative of sine inverse of x is equal to 1 over rad 1 minus x squared, which is this formula, first formula in our table. I'll do one more. I'll just do the derivative of arctangent. Arctangent and arcsine are the most commonly used ones, right? So let's start with tangent of tangent inverse of x is equal to x, just by the inverse definition. Then if I do the derivative of both sides, I get secant squared of tan inverse of x times d dx of tan inverse of x is equal to 1. And so d dx, or the derivative of arctan, is equal to 1 over secant squared of tan inverse of x. Okay, so let's think about how to find secant squared of tan inverse of x. We'll just draw a little triangle like before. We'll recognize that this angle, green angle, if I'm saying the tangent is x, then that would be x and 1 for opposite over hypotenuse, right? And opposite over adjacent, that's tangent. And so the hypotenuse would be equal to the square root of 1 plus x squared. Okay, so then in this angle, in this triangle, this green angle would be tangent inverse of x. It's the angle whose tangent is x. So that angle is tan inverse of x. So secant of that green angle is equal to hypotenuse over adjacent, right? Because we are flipping the cosine. hypotenuse over adjacent, and then secant squared of that will just take away the square root, and I'll get 1 plus x squared. So in my formula here, I can put 1 plus x squared in the denominator, and that's what the derivative of tangent inverse or arctan is equal to, right? So I've proved a couple for you. It's fun to try to prove some of the others. Like I said, the ones that I'll have you know for class are these three, and then the other ones, make sure you know them if you're taking the AP exam. Okay, let's do a couple examples. So if you're differentiating now a function y is equal to sine inverse of x, you're going to be using these new formulas, right, with all the old formulas that you already know. So this one, I would write it as sine inverse of x to the negative 1. You can also use a quotient rule, but whenever you can write something to the negative 1 power, that's going to be easier to do than the quotient rule. So y prime, so our inside function is sine inverse of x, and in prime is our new formula, and outside function is x to the negative 1, and out prime is negative 1 x to the negative 2, which I like to use it as negative 1 over x squared. It's just easier to handle that way. And so then if I do out prime of in, I'm going to get negative 1 over sine inverse of x, the quantity squared, right? That's out prime of in times in prime, which is 1 over rad 1 minus x squared. So if you combine those two fractions, it's negative 1 over rad 1 minus x squared times sine inverse of x, the quantity squared. Okay. This next one, x arc tangent x, find y prime. You can try to pause the video, think of it as a product, and see if you get the answer. So y prime is going to be first times the derivative of the second. So when I think of the derivative of arctan rad x is my inside and arctan is my outside. The derivative of arctan is 1 over 1 plus x squared. So I'm going to do 1. This is now out prime of in is going to be 1 over 1 plus rad x squared times the in prime, right? So rad x squared is just x. So I'm going to get really just this as my derivative of the second function. So first times the derivative of the second plus the second, which is arctan rad x, times the derivative of the first, which is just 1. So that's really the answer, and we might clean it up and just say x over 2 rad x times 1 plus x plus arctan rad x. Okay, last couple of examples. So here I have f of x is equal to sine inverse of x squared. So sine inverse is our outside function, x squared is the inside function. So f prime of x is equal to out prime of in. So remember, out prime is the new formula, 1 over rad 1 minus x squared. Out prime of in, the in is x squared already, so it's 1 over square root of 1 minus x squared squared, which becomes x to the 4th. So I'll have out prime of in times in prime, and I would just write it like this. Oh, x to the 4th. Okay, that looks very similar to sine inverse of x, the quantity squared, but the two things are different, right? In this one, the inside is sine inverse, and the outside is x squared. So for this one, the out prime is simply 2x, and the in prime is our new formula. So this will be out prime of in times in prime. And so we're going to end with 2 sine inverse of x over rad 1 minus x squared. Okay, so basically, what are our takeaways? They are, first of all, that if f is a one-to-one function and it's differentiable, right? Those are the two conditions. Then we have a new formula for the inverse. The inverse is g. The inverse is also differentiable. and its formula for g prime will be 1 over f prime of g of x. That's the first thing. Second thing is we have to remember our inverse trig formulas for the derivatives, and as I mentioned, I'm just holding you responsible in that class for the three arc sine derivative, arc cosine, which is just the arc sine with the negative sign tacked on, and arc tangent, right? So we'll work on those first, and by the time we get to the AP, for those of you who are taking it, we can also practice the other ones. So I can't wait to see you in class. I hope that all made some sense. It takes practice, so please just keep plugging away at it and have a great rest of your day.